Okay, so we are going to see a very nice example of finding the Jordan form for a matrix. So this will be very nice. Um, the Jordan form is like trying to diagonalize a matrix, but if it's not diagonalizable, so we can bring it to a form of blocks on the diagonal that is called Jordan form. The idea now is to take a matrix, and you see the matrix right over here, this A right over here, and find its Jordan form. You'll see that it's quite similar to finding the diagonalized form, just we can't diagonalize the matrix, so it will go to Jordan form instead of the diagonal form of a matrix because there is none. You will see, for example, that the eigenvalue that we will find, their geometric multiplicity won't be equal to the algebraic multiplicity, and therefore the matrix cannot be diagonalized, but it can be bring into its for Jordan form, which is maybe the closest thing, which is block diagonal form to a diagonalized form. So let's start. We start with the matrix, it's called A, and the step that we are going to take is finding the eigenvalues for the matrix throughout the characteristic polynomial. And after that, we will find the algebraic multiplicity and geometric multiplicity of each one of the eigenvalues. And then by that, we will be able to form the Jordan form. So here is the matrix. We are going to find the characteristic polynomial, the eigenvalues. You know how we are going to take the eigenvalues. We are building from the matrix this form A minus lambda I. And now we're going to take the determinant of this form. You see the lambda on the diagonal when we subtract it, and this will be the eigenvalues. In this case, there will be only one eigenvalue. Now let's take the determinant of this. We will open the determinant throughout the third column. It starts with a plus. So you can see plus minus plus. So it's 1 minus lambda and times the determinant of all what is left except for the column and row of this 1 minus lambda. So this is the determinant that we need to calculate. We calculate this determinant and we are getting for the determinant of a minus lambda I, lambda minus I 1 to the power 4. So this is the characteristic polynomial. Now, from this, we can right away, immediately, see the eigenvalue, which is 1. This is the root of this polynomial, the characteristic polynomial. And you can also see immediately the algebraic multiplicity of this eigenvalue, which is 4. This is the power of this eigenvalue. You can see the 4 right over here. And this means that all the, let's call it the degrees of the blocks for this eigenvalue in the Jordan form will be sum to 4. Okay, so now we need to find, after we found the algebraic multiplicity of 4, we need to find the geometric multiplicity. So what we need to calculate now is the kernel of a minus I, and we are going to do that. And a minus I, because the eigenvalue is 1, so we are subtracting 1 times I. And the kernel will give us the eigenspace, and the dimension of the eigenspace will bring us the algebraic geometric multiplicity. You can also find it throughout calculating the rank and then doing n, which is the order of the matrix, n minus rank of a minus I. Remember that the matrix is square. We are dealing with square matrices. Okay, so let's find the geometric multiplicity for the eigenvalue that we found. A minus I, we are starting with this. In order to find the rank, let's do a Gaussian elimination and get to a echelon form, and by that we'll very easily see the rank of the matrix because the amount of rows that won't be zeros will be the rank of the matrix. So let's do some Gaussian elimination. You can see here the Gaussian elimination. We start by multiplying by minus third, swapping rows, and etc. Until we get to reduced echelon form like you see right over here. This is the reduced echelon form. You can see that one row became total zeros, and we have 3 rows that was not annihilated. So the rank of the matrix is 3. So the geometric multiplicity of the eigenvalue that we put, which is 1, is 3, because there are 3, the rank is 3, and now we're going to do n minus this rank, and this will be the geometric multiplicity, not 3. So n, which is 4, minus the rank of this matrix, which is 3, will give us 1. This is the dimension of the kernel of A minus I. This is the geometric multiplicity, which is 1. So here it is. Geometric multiplicity is 1. Sorry for the 3 that I said. Great. Now we can determine the Jordan form, which by using the geometric multiplicity, which tells us how many blocks of this eigenvalue there are. In our case, the geometric multiplicity is 1, and so we know that there is only one block for this eigenvalue, and also we know that this is the only eigenvalue. Therefore, it's very straight away. We have only one eigenvalue, that is 1 and one block. So I just put one block of Jordan block, and because it's a block of 4 and 4, therefore I need to put ones above them. Okay, so this is it. This is the Jordan form of our matrix A. And you saw in this case, we only needed the geometric multiplicity and algebraic multiplicity. We sometimes need more. In this case, it's straight away because we have only one eigenvalue and only geometric multiplicity of 1. So we have only one choice. We don't need any more. In order to know how the Jordan form will look, this is the Jordan form of our matrix. Thank you very much. And this is how we managed to do all the steps in order to get, in this case, this was enough to get the Jordan form. We found the characteristic polynomial, the eigenvalues, the algebraic multiplicity, the geometric multiplicity, and by that we could conclude, in this case, not always, the Jordan form of this matrix. Thank you very much. Thank you for watching. If there are any mistakes or correction, please tell me. And that's it for now. Goodbye.